1. What specific problem does the WAC methodology aim to solve regarding the types of hallucinations in LLMs, and why is this differentiation important in improving the reliability of these models?
The WAC methodology aims to solve the problem of distinguishing between two types of hallucinations in large language models, LLMs, HK-, where the model lacks the necessary knowledge, and HK-, where the model has the correct knowledge but still generates incorrect responses. This differentiation is crucial because it allows for targeted detection and mitigation strategies tailored to the specific causes of hallucinations. By categorizing hallucinations accurately, the WAC approach enhances the reliability of LLMs, as it enables interventions that can either consult external sources for HK- cases or adjust the model's computation for HK- cases. Furthermore, the methodology demonstrates that model-specific datasets are more effective for detecting HK- hallucinations than generic datasets, highlighting the importance of understanding each model's unique knowledge and hallucination patterns. Overall, this nuanced understanding of hallucination types contributes to the development of more robust and dependable LLMs.
2. Can you break down and illustrate step by step how the WAC methodology constructs a model-specific hallucination dataset, particularly focusing on how examples are categorized into HK $, and HK $+?
The WAC methodology constructs a model-specific hallucination dataset through a systematic process that categorizes examples into two distinct types of hallucinations, HK- and HK-. First, the process begins by evaluating the model's responses to a set of questions. If the model fails to generate the correct answer in any of its attempts, the example is labeled as HK-, indicating a lack of knowledge. Conversely, if the model generates the correct answer consistently, it is classified as a high-knowledge scenario. Next, within this high-knowledge category, the examples are further analyzed to determine if the model hallucinates despite having the correct knowledge. This is done by modifying the prompt using techniques such as persuasion and weak semantics to induce hallucinations, leading to the classification of these instances as HK-. Thus, the WAC methodology effectively differentiates between hallucinations caused by insufficient knowledge and those arising from incorrect generation, despite possessing the necessary knowledge.
3. Provide an illustrative example of the WAC method in action, walking through the process beginning from a given question to how a potential hallucination is categorized as HK $, or factually correct.
To illustrate the WAC method, consider a closed-book question answering CBQA scenario where the model is asked, "What is the capital of France?" The model generates an answer, say Paris, which matches the factually correct answer. This instance would be categorized as factually correct. However, if the model is prompted with a similar question, "What is the capital of Germany?" and it generates Berlin, but then in a subsequent altered prompt produces Munich, despite knowing the correct answer, this would be categorized as HK-, because the model hallucinates an incorrect response despite having the correct knowledge. The WAC method involves first identifying whether the model has the necessary knowledge by checking if it can generate the correct answer in a standard prompt. If it can, the next step is to alter the prompt to induce potential hallucinations, allowing for the classification of the output as either factually correct or HK-, based on the model's performance in this new context.
4. What theoretical or practical advantages does the WAC methodology offer over existing approaches when it comes to detecting knowledge-based hallucinations, especially in terms of model performance and reliability?
The WAC methodology offers significant theoretical and practical advantages over existing approaches in detecting knowledge-based hallucinations by providing a clear distinction between two types of hallucinations, HK-, lack of knowledge, and HK-, hallucinations despite knowledge. This differentiation allows for targeted detection and mitigation strategies tailored to each type, enhancing the reliability of the detection process. Additionally, WAC constructs model-specific datasets that capture unique knowledge and hallucination patterns for different models, which improves detection performance compared to generic datasets that conflate these causes. The experiments demonstrate that classifiers trained on model-specific datasets achieve higher accuracy in identifying HK+ hallucinations, indicating that the methodology effectively captures the nuances of each model's behavior. Furthermore, WAC enables preemptive detection of potential hallucinations based solely on input queries, a capability that generic datasets lack, thereby enhancing the overall reliability of model outputs.
5. Discuss the experimental design used to validate the effectiveness of the WAC datasets. What metrics and benchmarks were applied, and how do these demonstrate the technique's robustness?
The experimental design to validate the effectiveness of the WAC datasets involved several key steps, focusing on distinguishing between hallucinations caused by lack of knowledge, HK-, and those occurring despite having knowledge, HK-. The researchers trained classifiers on the model's inner states, specifically using a linear classifier to detect different types of hallucinations, with a dataset split of 70% for training and 30% for testing. Metrics included detection accuracy across three classes: factually correct, HK+ and HK-, with results showing accuracy rates of 60% to 70% at the highest model layer, significantly above the random baseline of 33%. Additionally, the study compared model-specific datasets against generic datasets, demonstrating that classifiers trained on model-specific datasets consistently outperformed those trained on generic datasets, indicating the robustness of the WAC approach. The findings were further supported by Jacquard similarity measures, which highlighted the unique knowledge and hallucination patterns across different models, reinforcing the necessity of model-specific datasets for effective hallucination detection.
6. What limitations or challenges did you encounter in your work with the WAC methodology, and what future directions do you suggest to address these drawbacks or further extend the research?
In our work with the WAC methodology, one significant challenge was the inherent complexity in distinguishing between hallucinations caused by a lack of knowledge, HK-, and those occurring despite having knowledge, HK-. This differentiation is crucial for effective detection and mitigation strategies, yet it requires a nuanced understanding of the model's internal states, which can be difficult to interpret. Additionally, while we demonstrated the generalization of HK+ detection across different prompt settings, the performance drop of up to 10% when switching settings indicates that further refinement is needed to enhance robustness. Future directions could involve developing more sophisticated models that can better capture the subtleties of hallucination types, and exploring additional synthetic setups to enrich the dataset. Moreover, expanding the WAC methodology to include a broader range of models and tasks could provide deeper insights into the variability of hallucination patterns across different contexts.